Hey guys, welcome to lecture number 29. Yes, that's 29, I know for sure. Well, this will be the last lecture in this course. And in this lecture, we will be talking about numerical integration formulas. You will see a method on how to compute, in fact, not to compute for those integrals which cannot be computed. You will learn a method on how to approximate those integrals for certain functions. And you will see how close different methods, different integration methods will be to the exact value of an integral. And we'll see a trivial example. Well, an easy example where we will apply different methods of integration formulas, and you will see how well they can approximate an integral. Well, usually this lecture is not required for the final exam, so you can stay relaxed about this one. But on the other hand, I would suggest you watch it, you have a very good look at it, because it might be useful for other classes. For example, when you take Calculus 2, you will be interested in this numerical integration formulas, or when you will take differential equations even, you'll learn about these formulas. But also those of you who want to go deeper into mathematics, they can find these formulas, these integration formulas, in a numerical analysis course. All right, so I think we can get started now, and let me just dive in directly into the subject. Well, it will be I would say a pretty long lecture, but all right. But like I said, it's a very important lecture, and those of you who were interested in this subject, I think you'll find it very useful and very nice as well. Usually, I would like to say one thing. This is not usually covered in any Calculus 1 material at other institutions. That's a little bit surprising for me to see that the tech, they actually, well, I'm surprised in a good way, I would say, that the tech, they actually care about this numerical integration formulas. All right, so let's see what this is all about. Let me just go back to what the integral actually is, right? So remember that the integral, right, is just the area under the graph. So if we have something like this, right? Look, let's say this is the graph of f. Look at this side here. So if this is the graph of f, and let's just say we want to measure the area bounded by these two numbers, a and b. So we know that, well, in this case, the function f is non-negative, right, on AB. It's quite obvious to see that. Well, we know at this point, based on everything we have discussed, that the integral, this number, the integral from a to b of f of x dx, is nothing else than just the area under the graph of f on that interval, namely on the interval AB. So in other words, the area, let me point out right here, this is the area under the graph, this is the integral. So this guy here. Right, so this is here the integral from a to b of f of x dx. All right, so we already know this. Great. So that's the definition. And now we would like to see how can we approximate that area. So that is the question we're interested in. So that, in fact, let me just put it here. Question, very important question. How can we approximate the area under the graph of f? in other words, how can we approximate this interval? And well, what methods have we learned so far? The first method that we learned, remember, we use approximation by rectangles. Remember that? So let's go back to this. So let's see, approximation by rectangle. So let me just look at the graph of f again. Look at this here. You see, this is the graph of f. And now I'm trying to approximate by rectangles. And the way I'm going to do it is just like that. Look at it. You see, I'm going to use the left endpoints, right? So I'm just going to divide the interval. Well, here in this picture, we have only, I divided it into 6 parts, right? So I have this part here, right? So this first rectangle, which is this part here, and you see there are some leftovers. Also, the second rectangle is this one here. Look at this, right? The third rectangle is this one here. Look at it. And the fourth one, then the fifth one, and then finally the sixth one. Right? So this is how we can approximate the area under the graph by using left endpoints, and just by using 6 rectangles. But in general, we can use n left endpoints. So imagine that instead of x0, x1, x2, x6, we have we have x0. So instead of x0 all the way to up to x6, we have x0 all the way up to xn minus 1. So we have n left endpoints. Well, clearly, if you look at the area, right, the difference delta x, which is usually is b minus a over n, right? If you just compute one area, it will be just delta x times f of x0. If you look at the second area, it will be delta x times f of x1 and so on. And when you add up all these areas, you will get this expression that you see here, which is an is delta x times, well, you can factor delta x, and then you will end up with the sum of f evaluated at the left endpoints, right? And this is what you get. So you get this thing here. That's the thing. But you see, I have a question for you. Based on, if you look at the picture, do you think it's a good approximation of the area under the graph? Look at this part here. You see, you're missing something. Look at this. This part here. You see, this guy here, you see? What about this part, or this part here? Or this one here, look. There are some leftovers here. So what are we going to do? We're going to miss this. All right. So bear with me so far. So based on the picture, do you think this approximation will be a very precise one? What does your intuition tell you? It will be too low. Something like this. You see, it's too low. So you have some leftovers here. So it is an approximation, but maybe it's not the best one. So maybe we can do something here. All right. Let's look closer here. What if we do by the right endpoints? And I want you to look at this picture. Well, basically, when we do by the right endpoints, it's the same thing. But anyway, look at let's suppose that the graph of f is like this. So what I'm interested in is to measure the area under the graph, right? So you see, I want this area here. How should I put it? Okay, let me just say I want this area here, you see? So between A and B. So that's the area I want. So that's the area under the graph, right? So that's this is what I want. You see, the thing is that exactly, it will be too low because if I approximate by rectangles, and let me just look at this here. Look at it. You see, this is the first rectangle. Look at it. Now let's look at the second one. So again, let me just give you the example with 6 rectangles, and let me look at the third one. Then this will be the fourth one. Here comes the fifth one. And now here is the sixth one. All right. So you see, there are some left. So it goes. So it doesn't approximate that well. You look at this here. So again, we have this part here. And again. So, but this is the approximation by right endpoints. You see. All right. So what are we going to do? So you see, again, by the right endpoints, the only difference now is that instead of from x naught all the way to xn minus 1, because those were the left endpoints, now I'm just going to use the right endpoint. And the right endpoint, as you can see, they're x1 in this picture, then x2, and then all the way to x6 or xn if you want to consider endpoints. So the area of each rectangle will be delta x times f of x1, the first one, then the second one is delta x times f of x2, and then you're going to add up all of them. You're going to factor delta x, and then you're going to end up with this beautiful thing here, right? This is the formula. So the area of the under the graph, if you want, will be delta x times f of x1 plus f of x2 plus all the way up to f of xn. All right. Again, it's not quite a good, it doesn't look, if you look with the graph, it doesn't look quite good. It's not the best approximation we can find. All right. But now, let's do something even better. I want to show you something. In fact, let me just go with a picture now. I want you to look at this picture. Okay, so look at this. Let me just consider the graph of f. Look at it goes like this. All right, so this is the graph of the curve y equals f of x, right? And now I'm interested in computing the area under the graph between these two. All right. But now let's look at a section. So let me consider this section, let's say, between xk minus 1 and xk. And if you look at this guy here, maybe this, well, of course I can approximate this by rectangles, but maybe I can do something better. Look at it, you see? Let's consider this differently. Let me just draw here a line. You see, this is a line. And maybe I can look at this guy in a different way. You see, if I draw that line there under the curve, so which will approximate the curve very good, I will end up with this guy here. Look at it. Which looks like what? Like a trapezoid, right? Ah. Well, the length of this one here is f of, right? This is let me just write it here. This is f of xk minus 1 And this guy here is f of xk. This is what you guys see here. And of course, the difference between xk minus 1 is just delta x, right? So that's the classical thing, the delta x. All right, so maybe we can do something with this trapezoid. So instead of approximating by rectangles, which is not quite accurate because it goes up, some extra, some surplus, I have up or down. So it's not a very efficient way to do it. So maybe I can use trapezoids. So that's what I'm doing. And let me just compute the area of this trapezoid. If you look at this, the area of this trapezoid here, what is the usual area of the trapezoid? Do you remember that? So is what? Is 1/2, right? Times f of xk minus 1 plus f of xk times delta x, right? Which is the height. Pay attention, this is a right angle trapezoid here. So this is the height, which is delta x. So it's the big basis plus the other basis, the above basis, times the altitude, everything over 2, which is exactly the area of the trapezoid. So for this section, for this trapezoid, the area will be, let's just say, it will be 1/2 times f of xk minus 1 plus f of xk times delta x, right? Does it make sense? So that's the area of the trapezoid. And now let's apply to our problem. So let's look at all areas, all right? And let's just add them up. So this is just for one section, right? That you see in the picture. And then when we add them up, guess what? We can approximate this. So the area of the entire thing, which can be approximated, right? So we can do the same thing, I don't know, here, for example. Look, but let me just do it with a different color. Look at this guy here. You can do the same thing, you see? You see, again, you have a trapezoid, then you do the same thing here. Again, you'll have a trapezoid, and so on. You see, you don't lose too much here, it's just by a little. So as you have a curve, you go like this, as much as you can try to stick closer to the curve as much as you can. Sometimes it works well by using just rectangles, but when the curves go like this, maybe it's better for you to use the trapezoid. So the entire area, if you add it up, it will be delta x over 2 times f of x naught plus 2f of x1 plus 2f of x n minus 1 plus f of x n. All right, so and now let me just tell you about the trapezoid rule. What is this all about? You see, basically the area is this. So maybe that would be a good approximation. This is a good approximation for the integral, right? For the integral from a to b of f of x dx, since the integral is the area under the graph. Well, and now let me just say directly, this will be summed up in this amazing rule, which is called the trapezoidal rule. And basically tells you the following. It tells you that if I have a continuous function, right, on the interval AB, right, the real valued continuous function defined on the real on the closed interval AB, then we can approximate that integral. So in other words, the integral from a to b of f of x dx is approximately the area of the sum of all areas of trapezoids, right? In other words, this integral will be approximated by delta x over 2 times f of x naught plus 2f of x1 plus so on 2f of xn minus 1 plus f of xn. So that's the trapezoidal formula. It's pretty nice. And once again, it's just by look at this here, right? You see this is all right. Of course, delta x is b minus a over n. So for a larger n, as n grows larger, right? This is getting even a better and better approximation, right? Okay. So this is the trapezoidal rule. So you see, this is a bit more efficient than just approximate by rectangles. And now let me see, what about the error? In fact, let me just ask the question. What about the error? In the trapezoidal that is the question I want to ask. All right, and now let's talk about. So let's see the error. As you can see, en, this en is nothing else than just the difference between the integral and this whole thing, delta x over 2 minus times that. So then we have the following. Well, if f has a continuous second derivative, right? In other words, we call these functions of class C2 functions, right? It's just the class of functions which are twice differentiable and the second derivative is continuous. Well, as you know, that if we have a continuous function, then on a closed interval, then that function has a minimum and a maximum. So those can be attained. And moreover, the error, the estimate of the error term is b minus a cubed, everything over 12n squared times the supremum of the second derivative in absolute value. So that's the error estimate, which is pretty good if you look at it. You see, as n grows larger, the limit will be quite obvious, will be 0. So let me just point out this remark: as n goes to infinity, then en goes to 0. So en, that integral for, so this integral here, right, dn is the difference between this integral and this term here. So for n large enough, this will be a very good approximation. All right, so that's the error term. And now let me just give an example. And I would like to think example 1. All right, let's see. So the question is the following. How many intervals are needed to approximate this integral, the integral from 1 to 2 of 1 over x dx, using trapezoidal rule, and to guarantee the estimate error will be within 0.01? So that is the question. First, before we even apply, like I said, I would like to apply this rules, the rectangle rule, the trapezoidal rule. I would like to apply them to some elementary functions. And now, first, let's see about this one. So what do you think of this one here? This integral from 1 to 2 of 1 over x dx is what? Can you give me the exact value? What is it? Come on, tell me, what is it? what? Is ln of x from 1 to 2, which is ln of 2 minus L over 1 by the fundamental theorem of calculus. Wait, let me just say fundamental theorem of calculus, which is ln of 2. Approximately, this is 0.69. So let's keep this value in mind. And we would like to see, when we apply the trapezoidal rule, we like to see how close is the estimate using trapezoidal rule. How close is this to the actual value? All right, let's see. The question is if is f second prime continuous on 1, 2? That's what we want to see. Well, look at the derivative, the derivatives. So the first and the second derivative, right? So the first derivative for the function f equals 1 over x. So f prime is negative 1 over x squared, and f second prime is 2 over x cubed. Great. So I'm going to consider the maximum value of the absolute value of f second prime of that interval. Well, the function is continuous, so I have no problem. So the maximum will be 2. And guess what? I can use the theorem above and I can estimate the error. So in this case, it will be, well, b equals 2, a equals 1. So, and since m is 2, then the error estimate will be 1 over 6 n squared. But now I would like to see, you see, I'm asked to, look at this, I want this estimate error to be within 0.01. All right, great. Then I just need to solve this in equation here. And once I do this, I'll get that n has to be greater than 4, something like 4.08. Anyway, this is just algebra. You guys can do by yourself as well. All right, let's see. Any questions about this example? Right, if there are no questions, let me show another rule. Well, let me show what we call a Simpson's rule or parabolic rule. You see, what if there, I showed you sometimes you can approximate by rectangles or only by rectangles, let me be specific, by using left endpoints or by using right endpoints. But as you have seen, the approximation is not the very best one. Or sometimes we can use trapezoids to get even a better approximation of the integral. But sometimes this is not the perfect one as well. Far from that. But what if there is a rule which combines the two? So basically, the rule will tell you I use rectangles when I want, when it's good for me, and then I use trapezoids when it's good for me. Is what is the best option for me to do so. And this is what we will call Simpson's rule or parabolic rule. So imagine that the graph of f is something like this. Look at this here, right? I'll have something like this. All right, and now I'm going to have these points. Let's say you have here x0, this is x1, x2, and so on. All right, so we would like to approximate this in a better way. Let's say in a parabolic way. So let's look closer. Again, look at this graph here, right? And now we would like to look at this very carefully. Usually, the area under the parabolic curve on the interval, let's just take here I have again 6 points, right? well, let me just see, this starts from, this is x naught, which is A, and it will end up here, which is B. And again, I have 6 endpoints here in this picture. But if I consider n endpoints, then, and if I want to look like, let's just say on the parabolic curve between x sub k minus 2 and x sub 2k, then the area, right, of A of x is 1/3, right, times f of x sub k x sub 2k minus 2 plus 4 f of x 2k minus 1 plus f of x 2k times delta x. So that's the area. All right, great. And now the only thing we are left to do is just to sum up all of them, all these areas under the parabolic curve. And then guess what? We'll have Sn. So I'll denote this the Simpson Rule by Sn, which is delta x over 3 times f of x naught plus 4 f of x1 plus 2 f of x2 plus 4 f of x3 plus so on, 4 f of xn minus 1 plus f of xn. So that's what we call the Simpson Rule. In other words, let me just say it directly. So if I have a continuous function on AB, basically the Simpson Rule tells you the following. The integral from A to B of f of x dx can be approximated exactly by this guy here that you see, by Sn. That's what we say. So basically this rule here, it says nothing else than just the fact that the fact that this integral is approximated by Sn, which you'll find here. Well, the error term, which will be given by the difference between these two, as we n gets larger, right? As we have n to be large enough, then the approximation gets better, obviously. And let me just talk about the error. So this time the error will be the following. So En, which is in absolute, sorry, if you want. So we will have that this difference will have this estimate, b minus a everything to the power 5 over 180 and to the 4th times the supremum, right? Let's just say sup of f, the 4th derivative of x when x is in AB. Well, provided that this guy is finite, right? We have to assume that. So that's the error term. This guy that you see here. Let's compare this. What do you think? Do you think this error term is better than this one? And pay attention, the function is than this one. Look at this one here. So maybe, well, I assume more for the function. I assume the function is 4 times differentiable, so it's a C4 function on AB. In this case, when I apply the trapezoidal error rule or error estimation, I only assume that f is of class C2. So you see, I assume more, but I get better. Great. And now, let me just do a summary. Look, what have we done so far? So what we covered is, at this point in this lecture is the following. So first, we try to approximate the area under the graph by using rectangles? Well, you have two choices here. You can either use the left endpoints or the right endpoints. It doesn't really matter. Then the area will stay basically the same. So both of them will approximate the integral. Well, unfortunately, it's not the best approximation you will find, but there is one. So it is an approximation. So those are the two rectangles rules by just using the left endpoints or the right endpoint. Now, the second one is by using trapezoidal rule. And in this case, you see an approximation which is better. You see that number Tn, which is delta x times f of x0 plus 2 f of x1 plus f of xn minus 1 plus f of xn. But even better, you can use Simpson's rule, which is nothing else than just a combination between trapezoidal rule and rectangle rule, which is given by that formula that you see. All right, so in summary, we have covered this. And now maybe we should do an example. And let me just do the following example, and I would like you to to think of it for a bit. So let's just use n equals 4. So we'll have n endpoint, and we'll divide the interval a, b into 4 endpoints. And then I would like to estimate this integral from 0 to 2 of x squared plus 3. But first, so we want to see, we would like to estimate this by what? By rectangles first. We'd like to see what happens there. Then I want to estimate this by trapezoids. And then third by Simpson rule. And I'd like to see which one is better. Well, I have a question for you before we even start the lecture. What does your intuition tell you? Like, which one do you think that will approximate the best our integral? So what do you think? What does your intuition tell you? Which one do you think it will be the best? The first one, the second one, or the third one? Maybe Simpson, right? Because it's a combination. It takes what's the best, what's better in both of them. So maybe yes, that would be a good. All right, but first let's compute this integral. So let's compute it, and then we'll see which one gets closer to the exact value. So this can be written as the integral from 0 to 2 of x squared dx, as the integral from 0 to 2 of 3 dx. And this will give us, so the first one will be x cubed over 3 from 0 to 2 plus 3 times x from 0 to 2, which will be equal to 8 over 3, right, minus 0 over 3, which is 0, plus 3 times 2 minus 0, which is 2. 8 over 3 plus 6, which will give us what? 24. Oh, sorry, 26 over 3. So that's the exact value. And we'd like to see which of these three rules will get closer to this value. All right, let's see. First, let me consider the function. Let's see who delta x is, right? So usually it's b minus a over 4 over n, but in our case, n is 4. So it will be 1/2. And now let's see the endpoint. So we'll divide this into equidistant subintervals. So from 0 to 1/2, then from 1/2 to 1, then from 1 to 3/2, and then from 3/2 to 2. All right, great. Now let's compute the values of each one of them. So f of x naught will be 3, right? Because x naught is 0. For x1 equals 1/2, then f of x1 will be 3.25. F of x4 will be 4, and so on, right? And you'll see you have a bunch of numbers here. Look at this, right? 1, 3, 3.25, 4, 5.7. All right, now let's do it by rectangles. And let's use the left endpoint. In other words, we'll use this formula, right, with the left endpoint. Then we're just gonna, it'll be 1/2 because delta x is 1/2 times, and we're gonna add all the left endpoints. So it's 3 plus 3.25 plus 4 plus 5.25, great. And it will give us this number here. So let's keep this number in mind. Maybe it will be close to this one here. Who knows? All right. Now let's see with the right endpoint. So instead of the left endpoints, I'll use the right endpoints. And then I'll have, it will give me, again, 9.75. Wow, what a difference. Wow, there's a difference between them. But we don't know which one. Well, we can actually look at the exact value. But anyway, let's see. Now let's use trapezoid. Again, we're going to use a trapezoid rule. So T4 will be delta x over 2 times f of x naught plus 2f of x1 plus 2f of x2 plus 2 of x3 plus f of x4. And then just algebra, because we already know the values, we're going to plug them in. And then at some point, it will give you 8.75. So we have another value. Wow. So that's a trapezoidal rule. So far, what did we get? So we get 9.75 using right endpoints, 7.75 using left endpoints, and then we got by using the trapezoidal rule 8.75. And you are like, whoa, which one is it? Well, let's use Simpson's rule. So by using Simpson's rule, and just by doing the same thing by replacing this, right? So Simpson's rule, which is this thing over here, right? You'll get, by doing the algebra, 8.6666. Oh my God. I want you to tell me which one is closer to the exact value of the integral. And in fact, we know the exact value. So what is this? This is what? Approximately, what is this? Can you tell me? 26 over 3 will be what? So if you do it with a calculator, it will give you what? Tell me. 26 over 3 is what? 8.6667, right? Which one is the closest one? Let's see. The first one, using the rectangles with left endpoints, was we got 7.75. Then using the same rule rectangles but with right endpoints, it was 9.75. Using trapezoids, I get 8.75. But using Simpson's rule, oh, guess what? I'll get this 8.666. So now let's compare them. Oh, look at them. All of them are here. And now you will see that the Simpson rule was the closest one to the exact value. So this is the closest to the exact value of the integral. All right, you see the exact value is 8 plus, so which will give us what was it? 8.667, right? Oh, wow. Look how close this is to this one here, right? So again, I want you to look at these. Anyway, you will see the details. If you want to do the computations by yourself, you're more than welcome to do so. So as you can see, I gave you just an example, it's a very simple example of how to compare these rules, or these 3 rules, let's say. Guys, I think I'm gonna stop here. Well, I rushed through things a bit, but I'm sure you got the picture, and I believe you can go over the video if you want to. Well, this is the end of the class of the lectures. Basically, we still have one more to go. We have a review session before the final exam, which will happen on May 9th. And by the way, pay attention to the time. The time is between 1 and 3 p.m. Well, unfortunately, I have something to do at later on in the evening. So I apologize for changing the time. So it's between 1 and 3 p.m. Central Time on Sunday, May 9th. So that will be the very last, our last encounter before the final exam. Well, with that being said, I'd like to thank you very much for this wonderful class. I think this was my last time teaching here at Texas Tech. And I wish you my very best in your future endeavors. And I hope all of you will become very good engineers at some point. But before you achieve that, make sure you take this undergraduate career very seriously. Because these are the best years of your life here. Well, perhaps those of you who want to go to graduate school as well, but so this is the best time for you to learn. All right. Well, I'll stop here. Feel free to stop by my office hours if you have any questions in like 20 something, 26 minutes and stuff, something like that. Well, you're more than welcome to join the review session next Sunday. So that will be our very last encounter. All right, guys, thank you very much. And I'll see you later on. Bye-bye.